Hi everyone, and welcome back. In this video, we're going to be looking at a couple qualitative methods in order to assess the distribution and/or normality of a random variable via the sampling process. In case you aren't already aware, several of the hypothesis testing strategies that involve z, t, chi-square, and f distributions are often based on the assumption that the distribution we are sampling from is normally distributed. There are other different types of tests that assume some type of distribution, so we should have some way in order to assess that distribution or assumption of that random variable that we are sampling or modeling. So let's try and answer this by looking at a couple one-dimensional scatter plots of some data, and let's see if we can sort of assess the type of distribution that we see here. So the first example that I want to look at is a data set that looks something like this. So x's are going to represent data points. So if you have a bunch of data points over here and then they sort of start to scatter as you move to the right side of this number line, what type of distribution do you think this would represent? So this is typically what we refer to as a skewed right distribution, and if we look at this from a histogram perspective, you'll probably see something similar to this, like a chi-square distribution. Now, if we look at another distribution, so let's look at this one. If we have some scattered points, let's do it in blue, and then they start to cluster as you move to the right side of the distribution, what type of distribution would that be? That would be a skewed left distribution or a negative skewed distribution. So that would sort of look like, not like that, but more like this. Right? So you have a tail on the left hand side, most of the data is on the right hand side. Let's look at this particular data set. So take a guess at what type of distribution this will be. Any idea? This would be a uniform distribution. So pretty much all values are equally likely to come up. So if you were to look at a histogram of this type of distribution or a box plot, the boxes would have relatively the same exact heights to one another. So a uniform distribution is usually what we refer to that as. What about something like this? So you have a couple clusters on the tails, and it sort of scatters in the middle. So what would that be? So if we would look at a two-dimensional plot, it would sort of look like that. So that would be a bimodal distribution. And lastly, the one that we're going to be focusing on, let us assume we have tails and we have a heavy distribution or density in the middle. Right? So this distribution would look sort of like that. Right? So what type of distribution would that be? So that would be a unimodal or a modal distribution. That of course would be a symmetric distribution. And of course our question is that a normal distribution? So quantile-quantile plots or QQ plots are ways to sort of assess the distribution of a particular data set. And normal quantile-quantile plots are used to assess the normality of a sample. So the guiding question that we need to answer is how to create an artificial, normally distributed data set of, say, size m. And I put normally in parentheses here because technically you can create an artificial any type of distribution data set that you want, and then you can construct what we call a quantile-quantile plot and to sort of see if the distribution follows that artificial distribution. So let's look at a particular example. Let us suppose that we have a sample size of size 7, and we want to see is that data set appearing to come from a normally distributed population. Well, if it is, then the two-dimensional scatter plot version of that would look like that. And if we have 7 random variables in that particular sample, then the middle one, or the median of that data set, should be at the middle of the normal distribution. So if n is equal to 7, that means x4 corresponds to the median of that data set. That means x3 and x5 should be close to the median, and then x2 and x6 should be a little bit more farther away in terms of differentials from the median compared to those inner numbers. And then x1 and x7 would be located farther in the tails. So that would be what we call an artificial normal or discrete normally distributed data set. Now, what can we say about the areas that correspond to each of these partitions? Right? So if these are truly normally distributed, that means the area in this tail would be equal to what? In particular, all of these areas should be equal to one another if this is indeed a normally distributed data set. So if we have 7 different points, that means it partitions this area into 8 different pieces. That means this is going to be 1 over 8, that's going to be 1 over 8, 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 and finally 1 over 8, and of course all of them sum up to 1. Now, of course, they're not going to exactly be equal to 1 over 8 if it is a distributed data set, usually due to error, rounding, and several other reasons. But we hope that these areas are close to 1 over 8. So if those areas are close to 1 over 8, that means this first value should be the 8th or the first percentile, right? So the area to the left of this value should be equal to 1 over 8. The area to the left of this value should be equal to 2 over 8. So that means this is the 1 over 8th percentile, and the 2 over 8th percentile, that would be equal to the 3 over 8th percentile. That would be the 5 over 8th or 4 over 8th percentile, which is the 50th percentile, aka the median. That would be the 5 over 8th percentile, the 6 over 8th percentile, and finally the 7 over 8th percentile. So if we want to construct an artificially normal data set of size m, then xk should be equal to, at least in Excel, we already know how to do this, will be equal to norm.s.imv of k divided by n minus 1. So x2 would be equal to 2 divided by n plus 1. And why is it n plus 1? Because if we have 7 data points, we have 8 different regions. 10 different points will give us 11 different regions, and so on. So if we want to create a data set of size 7 that is discretely normally distributed, then using that Excel formula, you can find that this is going to be equal to, let's use capital N for normal, is going to be approximately equal to negative 1.15, negative 0.67, negative 0.32, 0.32, 0.67, and 1.15. Notice the symmetry in this data set. Oh, we're missing one. Where's 0? Let's fit in 0 here. Our 0 is missing. There it is. So there's our normally distributed or discrete normally distributed data set of size 7. Now, one could also use xk is equal to norm.s.imv of k divided by n plus 1, but not necessarily standard normal, but just normal. So norm.imv with some desired mean and some standard deviation sigma that you want. And of course, you will get a different data set, but the R value between this data set and the data set that you actually sample will be exactly the same. I leave that as an exercise to sort of verify the conditions for which that statement is actually true. So we're just going to be constructing an artificial standard normal distributed data set and then comparing it to a sample that we draw from a sample and seeing if they have some correlation between each other. Now let us take a look at an example to sort of see how we would carry that calculation out. So now let us take a sample from some population and let's assume that its values are given to be the following. So example 1. So our question is going to be, does S, and let's assume the numbers are 8, 9, 11, 17, 26, 37, and 60, appear to come from a normally distributed population. At least if you just look at this data set, you should be able to see that the differentials definitely increase as you progress along the data set from least to greatest. And it's very important to note that this set must be ordered or ranked from least to greatest, else the correlation is not going to make any sense. So in terms of the realm of hypothesis testing, the null hypothesis is that the distribution we're sampling from is approximately normal, with the two-sided alternative that the population we're sampling from is not approximately normal. So if we just look at a couple different metrics, for example, the mean and the mean is going to be equal to 24, and the median of this data set is going to be equal to 17. So remember, if the median is less than the arithmetic mean, then we have evidence to believe that the data will be skewed to the right. So it appears to be skewed right. Right? So if our question is to assess the normality of this distribution, we need some type of strength in terms of this skewness. Yes, the difference between these two is equal to 7, but is 7 a large number? And of course that really depends on the unit that you're actually considering here. So we need a statistical way of assessing the normality of the distribution, and one way is to use Quantile-Quantile plots. So is this skewness actually due to the distribution that we're sampling from? So we can actually pose a couple other important questions. Is this skewness due to chance? For example, this actually could be a normally distributed data set. It's just a subset of that set. Or is the distribution of PS, distribution of PX, actually skewed? That's what we want to answer, right? So what do we know? So what do we have is a sample of size 7, and what we want to do is plot S versus that normally distributed data set of size 7 that we obtained first, right? So we need the quantiles of that data set and the quantiles of that data set. So this is where the NQQ plot gets its name from. So it's normal quantile-quantile plot. So if we actually go ahead and plot this data set, so let's assume that's k equals 1, 2, 3, 4, 5, 6, and 7, and we go back to the other data set that we have, so 1, 2, 3, 4, 5, 6, and 7, and we pair these up one by one. So pair those two, pair those two, pair those two, pair the medians of those data sets together, so 0 and 17 would be matched together, 1.15 and 60 would be matched together, and so on. And then do a plot, you're going to get what we call a normal quantile-quantile plot. So if we do that, so let's do S on the horizontal and our normally distributed data set on the vertical, you will get a plot that looks something like that. So this is what we call the NQQ plot of S, right? Now, does this appear to be normally distributed? So if they are indeed a normally distributed sample set, well, Sn truly is a normally distributed data set, and our question is S also appearing to be normal? If they are truly both normal, then the correlation should be equal to 1, and we should not be seeing a pattern here. That is, we should be getting a line if it truly is normal. And when we're talking about we're talking about S. Now, if you see any patterns here, then that means the dataset does not appear to be normally distributed, right? So let's just formally write that down. So if the ordered dataset is from a normally distributed population, then the graph of the NQQ plot should appear to be linear. That is, R should be approximately positive 1. Now, generally speaking, we could consider the case where r is equal to negative 1, but we're ordering both of these sets from least to greatest, therefore there should not be any possible reason for why the correlation will come out to negative 1. So if you rank these data sets, both the normal one and the data set one that you collected from the population, our goal is to compare it to r is close to positive 1. Now, for our example, one can find that r is approximately equal to 0.9247. So if this is our correlation for our data set, now of course if we look at this graph, does it appear to be linear? Of course not, at least not to me, but one could argue that the correlation between these values is really close to 1. So the question that we need to test is this statistically close to 1, right? So an equivalent way that we can approach this problem from the hypothesis testing perspective, so remember we're trying to say that px is normal versus the alternative that px is not normal, can be phrased in this particular perspective that the correlation coefficient between S and the normally distributed data set is greater than or equal to some threshold value. Now let's call that threshold value 0.98. You can change this to whatever you want. It really depends on the problem and the data set that you're actually looking at. But this definitely should be close to 1. But this is what we call our threshold value, right? And an alternative is that the correlation coefficient between S and our normally distributed data set is less than 0.98, or our threshold value of choice. Now, how can we test this particular perspective? Well, we do know a test statistic for the correlation coefficient. We know that the test statistic for rho is actually going to be equal to r minus rho 0 all over the standard error of the estimate of r for this particular parameter rho, with a degrees of freedom equal to n minus 2, where the standard error for r, so with standard r equals 1 minus r squared all over n minus 2. So we need a level of statistical significance in order to compare our, for example, our p-value to, but I'm just going to leave that open to you so you can sort of choose that based on your studies. So if we want to reject this claim, so if we want to reject the claim that it is truly normally distributed, then we want r to be significantly less than our threshold value of 0.98. If that is the case, that means what? That means we want our r value to be significantly less than rho 0. So if that is true, so that means this is like something really small, like 0.1, and this is like 0.98. That means the test statistic should be significantly negative. If that is the case, that means t-stat should be significantly less than 0. So if we look at our distribution for our t distribution, and remember this is a t distribution with n minus 2 degrees of freedom, so in that case this is going to be a t5 distribution. If we want a test statistic that is significantly negative, that means in terms of our one-sided hypothesis test, this is going to be our region of confidence, right? So that means we want a test statistic over here somewhere, and there is our one-sided t critical value there, and then of course our alpha value is located in this particular region, and our p-value would be the area to the left of our test statistic. So if that is the case, our test statistic t-stat we can find to be equal to negative 0.3248. So where does that come from? So you plug in your r value, your n value, that gives you your standard of error. Our threshold value is going to be our rho 0, and r, again, is our correlation coefficient between S and Sm. Once you have your test statistic, then we can go ahead and calculate our p-value, our one-sided p-value, and one can find that the p-value is approximately equal to 0.3792. Usually people use 5% as a cutoff value, but generally speaking, this is pretty large. So if we have a large p-value, that means we failed to reject the null hypothesis that px is indeed normal, which sort of contradicts what our observations were from our normal quantile-quantile plot. So why is that the case? Because this is misleading because n is small. Right? So if your n is small, I definitely highly recommend just looking at the quantile-quantile plot and actually not going through a formal hypothesis test, because the hypothesis test is usually going to give you misleading results when your size of n is significantly small. Right? Now, if we can do a little bit of simulation here. So if r was still, let's assume 0.9247, but n was equal to 200, you can find that the p-value would be approximately equal to 0.0476. And if you follow the 5% standard, then that would be significant evidence to assume that the distribution is not actually normal, which then would agree with our assumptions from the normal quantile-quantile plot. Also, if we know capital N, that would help too. Because if we know the capital size n, the population size, that means we can include the finite population correction factor into our standard error formula, which would definitely help reduce our type 2 error for our hypothesis test. Also, keep in mind that most of this discussion is based upon looking at this distribution, and this distribution does appear to be relatively like exponential or quadratic. Just because it looks like that does not mean that that is truly the case. Because if this is truly our data set, and we actually zoom out or collect more points, then it's possible that this region here corresponds to this little piece here, right? Now, if we look at this particular data set, does it look linear? No. But the second data set, most people would agree that yes, that looks at least a little bit more linear compared to this first thing. So this first quote-unquote non-linear data set could be the beginning or a subset of a truly linear trend. So keep in mind that is one of the downsides of statistics. But with those things in mind, let us look at another type of plot called a residual plot that is used to assess the distribution of a particular data set. So up to this point, what do we have? So we have that if a data should appear to be normally distributed, then the correlation between that data set and an artificial normally distributed data set should appear to be close to linear, i.e. the correlation coefficient should be close to +1 if it's ranked from least to greatest. If that is truly the case, that means a line should be the best fit model for that particular data set. So if we look at our data set from before, and a lot of people would say that this doesn't appear to be linear. So if we do a line of best fit and look at the points around it, they should appear to be scattered around that line in a random fashion. So if you qualitatively assess that this does not appear to be not linear, and you should be able to compare that to some other data set. So if you have, for example, this type of data set, and you were to have some line that fits the model, right? Then the points around it should appear to be relatively linear, if that is the case. So if we look at the residuals of our particular data set, then the residuals should appear to be scattered and we shouldn't get a problem. For example, if we look at these residuals here, they're all going to have a positive residual there. These are going to give you a negative residual, and then these are going to give you a positive residual where the residuals are increasing as you move along that line. So the residual plot analyzes the residuals for a particular plot associated to a regression line. So keep in mind, this is S, this is our normally distributed data set S. So what we want to do is we want to compare this to the linear regression line y hat for a normal quantile-quantile plot. So if we look at this particular residual plot, then we're probably going to have something like this. So every time you look at the residual plot, so this is the residuals of S versus S, where the residuals in the line of best fit is generated from the normal Quantile-Quantile plot, appears to be nonlinear or non-random, moreover, then that is going to imply that the data set actually is not coming from a normally distributed data set. So if we look at the residual plot of S and the residuals for S, and then look at the scatter plot for those points, then the points should appear to be scattered around the vertical line. So you shouldn't be able to see any pattern for the residuals if a line truly is the best fit model for that particular line, right? So if that is the case, that means our equivalent null hypothesis. So if this is the goal that we want for S is approximately normal, that means an equivalent null hypothesis would be that the correlation coefficient for the residual plot should be approximately equal to 0, with a two-sided alternative that the residual plot should be not approximately equal to 0. Now, you can find that the R value for the residual plot for the example that I gave before is approximately 4.13 times 10 to the minus 16, which a lot of people would agree is approximately equal to 0. But this misleading assumption is most likely guided by the small sample size that we gave. So always use a combination of both metrics and qualitative methods to assess the normality of your normally distributed population. So let's just summarize several of the things that we've mentioned up to this point, and then we're going to go through an Excel demonstration of how we can do this in Excel. Okay, so residual plots. So residual plots allow us to qualitatively assess if a line is a good fit for a data set XY. Keep in mind, generally this video topic is focusing on the normality, but technically you can assume this is a way to test the goodness of fit for a linear regression line. Now, in terms of the normal Quantile-Quantile plot, so NQQ plots allow us to qualitatively assess if the sample set that we collected from our population, let's call it PX, is coming from a normally distributed data set. And the residual plot for S and our normally distributed data set of size N allows us to see if there is not only a normal distribution that is associated to the data set, but any distribution moreover. So it allows us to see if there is a non-normal distribution for our data. That doesn't look like distribution, does it? So distribution. Right. So residual plots, normal Quantile-Quantile plots definitely have their individual purposes, but when you combine them, it does allow you to see if there is a non-normal distribution. So if you do look at your residual plot and you do see a quadratic pattern, that usually does imply that there might be a quadratic relationship between your X and Y data. And if that is the case, that means that the data set that you are actually sampling from is possibly coming from a parabolic or a radical type of distribution, and you definitely should investigate those types of things. So now that we know some of the theoretical basis for these things, let's go to Excel and actually do a demonstration of how we could construct a normal Quantile-Quantile plot and a residual plot for a randomly set of data in order to test the normality of that particular data set. So the first thing that we need to do is simulate some random sample that were to come from some distribution. So let's assume that this is going to be some random number between, let's assume that the number is between 1 and 100. I'm just going to use the random between function because then the probability that it actually does create a normally distributed data set is actually pretty close to 0. There are normally distributed random number generators that you could use in order to simulate that type of thing, but I do not want that type of outcome, so I'm just going to use some random number. So there's some random number, let's call it 38, and let's click and drag that down, and that's going to give us a normally distributed data set. So keep in mind that every time you do this, it's going to change the numbers every time you manipulate your data set. So what I want to do is just copy the values over and then delete those values so they do not change. So this is going to be my XK data set, and then I'm actually going to sort these values from least to greatest. So in order to do that, I'm just going to go up here to data, and then I'm going to click sort. Actually, I need to select my data set and then click sort. And then I'm going to sort by my XKs, and then I'm going to sort from smallest to greatest, and that's going to sort my values from least to greatest. Once I have my ranked data set, I'm going to then create my indices. I'm going to start at 1, and then I'm going to add 1 to all of my values above it until I get the number of data points that I have in my data set. So in this case, I have 25 data points. Right. So that is my random sample. So this is my sample set S. Now what I want to do is actually create my normally distributed data set. So N XK. So remember, this is going to be equal to norm.s.inv of the index over the sample size plus 1. So that's going to be 26. So that's going to be my first normally distributed data point all the way up to the last, and that should be normally distributed. So the next thing that I need to do is assess the normality between this and this. So the easiest thing I can do is, of course, construct a scatter plot, and if you see this particular data point, the data set actually does look possibly to be linear, right? So if the data set does appear to be linear, then in fact this distribution might be coming from a normally distributed data set, which is actually a little interesting. So in order to truly assess that, I need to also look at the residual plot and maybe see if there's a pattern that I actually don't see, because this could actually be parabolic or exponential or something like that. So in order to do that, I need to calculate the slope and the vertical intercept of my linear regression line. You could do that by just going here and right-clicking, adding the trend line, and then displaying the equation on chart in order to get those things, but we definitely should be able to calculate those numbers manually so we can manipulate these values as we see fit. So the slope, remember, is going to be equal to the covariance between our x values and our y values all over the variance of our domain values, which we're assuming is going to be S, right? And of course, make sure those numbers match. And then our vertical intercept is going to be equal to the y value average. So y bar minus m times x bar, right? And that's going to give us our vertical intercept there. Right. So now what we want to do is actually calculate the predicted values or the height of each of these points associated to the linear regression line. So that's going to be y hat k, right? So this is going to be, so y equals mx plus b. So that's going to be m times x plus b. And of course, keep in mind that you need to anchor these before we drag them down, right? So those are our predicted values. So keep in mind this is our obtained values, this is our predicted values, and the residual is the difference between them, right? So the residual for xk, right? So let's do let's do yk minus y hat k. And I guess to make sure you're not getting confused, let's actually call these yk, right? So these are our residuals, right? So it's just going to be yk minus y hat k. And if you want to find the sum of squared residuals, you could easily do that here, right? So let's graph our residual plot. So actually, let's title this correctly. This is the normal quantile-quantile plot for our sample. And let's now calculate our residual plot. So that's going to be the residual and our data set. Let's do a scatter plot, right? So this is our residual plot for our sample, right? So now that we're looking at our residual plot, we actually do not see much of a random behavior of our data points. We definitely do see some type of structure behind these data points, and maybe you would have seen this in the scatter plot of our NQQ as well. Because notice that as you move towards the tail, in particular the right tail, the data points definitely do appear to act very sporadically, right? And you definitely see that in our residual plot as well. So that is our residual plot and our NQQ plot. So at least for me personally, from our NQQ plot, it might appear that the data sets do appear to be relatively linear, but when we look at the residual plot for our data set versus our NQQ, we definitely do not see a random sporadic behavior for our residuals. And in order for this line to truly be a best fit for our data set, these residuals definitely should appear to be random, which is definitely not good if we do not see that random chaotic behavior. So that is just an overview on how to test the normality and also the distribution of the data set that you are actually in the process of studying. So I hope you enjoyed, and I'll see you in the next video. Take care.